Hi, this video is about B-tree. So in the first part of the video, I'll show you how B-tree works. And in the second part of the video, I'll show you my own implementation of B-tree using C#. The source code, the link of the source code is in the video description. So let's get started. So let's do a brief review on B-tree. So in this video, B-tree actually means B plus tree. B plus tree is a variation of B-tree and is widely used in a relational database. So B-tree is a self-balanced multi-way search tree. So every node, except for the root, has at least k children. So every node has at most 4k children. So which means every node has a capacity. And this implies that every node except for the root is between a quarter full and full. So in some documents you see it's between half full and full. I want to make some change, make it between a quarter full and full. I'll explain to you why that's the case. So the root node has at least 2 children unless itself is a leaf. And all leaves appear on the same level, which means the same height for all the leaves. So for B plus tree, the leaf nodes contain data, and the non-leaf nodes contain the indices to find the leaf node. So let's see how B-tree is constructed. Before I go into the details, there is one statement I wish you to keep in mind, which is B-tree is doubly linked list. So I say it again, B-tree is doubly linked list. Later you will see, well, you may have known something about binary search tree. You can forget about it for now. Because later you will see B-tree is very similar to the linked list, and it's not similar to binary search tree at all. So to understand how B-tree is constructed, let's start from the simplest data structure to store collection, which is array. But the problem is obvious. For the array, the size is fixed. If you allocate a too big array, you waste too much space. Or the array may not have enough space because the size is fixed. And how about the resizable array, so-called vector or array list? Well, the problem is in an array, you want to support fast search, so the data has to be sorted in the array, which means if you do an insertion, the complexity is big O n. That's too slow. So how can we improve? We can break one big sorted array into many small sorted arrays, and each small array has a capacity. So then the small arrays are connected as a sorted doubly linked list. Then the size can expand and shrink easily by inserting and deleting nodes in linked list. So we know when we find the node, it takes big O1 to insert or delete a particular node. So when you search inside the node, because the small array is also sorted, so searching in the sorted array is fast. So it's inside the array is big O log k. So when you do insertion, you the complexity is big O k, because you may have to shift the small array. Later I will see it takes log n to locate the node. I'll see described later. So as long as the k is not a big number, the B-tree can be pretty fast. So here's the example how it works. So you have one big sorted array, start from one big sorted array. Then you break the sorted array into many smaller sorted array. Let's assume the capacity is 4. Then you connect those small sorted array into a doubly linked list. So each node has a pointer to its predecessor and to its successor. And also you keep a pointer to the head and another pointer to the tail. Well, the head doesn't have predecessor and tail doesn't have successor. And since the small, and also later I will show, each node, except for the root, must contain a minimum number of elements. So then, from the doubly linked list, you take the zeroth element for each small array, and then you compose a new array. So the zeroth element for each array serves as the index. Then you have a smaller array, and the size is shrinked by a factor of 4. In this case, we make the capacity of 4 for the small array. So for the smaller array, the size has shrinked by a factor of k. Okay, in this case, the k is 4. Then you can see you start from a long array. Then you have a smaller array with the size being shrinked. Then you do the same thing again, over and again. Then eventually you have only one node. So what you have is layers of doubly linked list. And each node has its capacity. In this case, capacity is 4 as an example. And each node contains pointers to its predecessor and successor, and its parent. And for the non-leaf nodes, it also has pointers to its children. And here is one thing I want to keep in mind: when you construct the B tree, the zeros element of the head node serves as a sentinel, and then you can see the sentinel is always promoted to the higher level and all the way to the root. These are the sentinels. So then keep this diagram in mind. It will help you understand the operation of the B tree. It's very helpful. Let's see how B tree works. So we use B tree to store the collection. So the first thing is how to search in the B tree. Search would be pretty easy. You start from the root. You always keep a pointer to the root, and you do binary search in one node at each level. Because each node's elements are sorted, you can do binary search, and then you get the result as a leaf node. For example, let's search the key value being 6. So in each of the nodes, you find the greatest index whose value is equal or less than the key you are searching. In this case, is 6. So you start from the root. The greatest index whose value is less than or equal to 6 is 0. Okay, so you go to its zeroth child, which is here. In here, you also search the greatest index whose value is equal or less than 6. In this case, the index is also 0. So you go to its zeroth child, it's here. Then in this child, the index, the greatest index whose value is equal or less than 6 is 1. Okay, it's here, it's 1. So you go to its child with the index being 1, is here. Then here's the leaf. You do the same thing. You find the greatest index whose value is equal to or less than 6. In this case, the index is 2. 0, 1, 2. The index is 2. And in this situation, the value at 6 equals to the key. So this is the search hit. You find it. You find the value. That's a search hit. So in case the leaf node is like this, 4, 5, 7, 8, then you search the greatest index whose value is equal to or less than 6 is 1. In this case, the index of the 1 is 5. 5 is not equal to 6. In this case, is a search miss. So this is how you do search. So the way is, let's also showing a way showing you a way to go from the root to the leaf quickly. So in each node, you do binary search. Then let's see how it works for the insertion. So you do the same thing from the root to leaf. Then here's the rule. If the node is not full, insert at the correct position, and then you are done. What if the node is full? Because each node has a capacity. Then you split the node. So you split the node means you add a new node after that node. So here is the example. This is the leaf. Assume you want to add 6 into this leaf node, but this leaf node is full. So what you have to do, you have to split this leaf node, which means you create a new node and append the new node to insert this new node after this node, because it's a linked list. You create a new node, you reconnect the pointers, and also you put the number 6 at the proper position, which is here. Then you have a new linked list. It's not a new linked list. You insert a new node as a linked list. This is at the leaf node. This is at the leaf. So then what you have to do is to propagate upwards. Here's an example. When you do propagation upwards, you have to update the parent. The parent is the original node of the parent. And if you update the index in the parent if necessary. What it means is that in this leaf node, you insert a new node at here, and then in the parent of this original node, you need to add a new element in this node. Why? Because the zeros index serves as the zeros element serves as the index. You have to insert a new index into this parent, into the parent node of this node. So in this case, the parent node is not full, so you just add an element into the parent of this node. Then you are done in this situation. But the propagation may go all the way to the root. What if the root is full and then you are trying to insert a new node into the root? Well, you split the root and then you have a new root. Here's the example. If the root is full, then you want to insert another element into the root. So you split the root and insert the value into the right position. Here is a 7. The index is 7. So you split the root node, and then you insert the value, index value of this new node into the proper position. Then you have the new root. You have to redirect the root pointer to the new root. So that's the insertion. So how about deletion? Well, deletion is generally more complicated than insertion. So let's go over the rules. You start from the root and go to the leaf, as I showed you before. If the element does not exist, this is at the leaf node. Okay, if at the leaf node this element does not exist, you do nothing and you are done. It's a search miss. You are deleting something that doesn't exist. Then you are done. If the element exists, that's a search hit. You delete it from the array in the node. You may have to shift the entire array. I mean the small array. So after the deletion, here's the thing. If the number of elements is greater or equal to the minimum, remember, for the B tree, except it's the root, it must contain a minimum number of elements. If the number of elements is greater or equal to the minimum, then that's okay. So if the deleted index is not 0, you are done. Okay, you don't need to do anything. Otherwise, you need to propagate upwards to update the index. Why? Because if the index is 0, the zeros element serves as the index. You have to update its index in its parent node. So in this case, the node is not full. The number of elements is greater or equal to the minimum after deletion. So what if the number of elements is less than the minimum? Then you break that rule. You have to fix that violation. So how to do that? If the node has no predecessor or successor, which means it's a root, that's okay. The root is allowed to have number of elements less than the minimum. If it's a root, if it happens at the root, you are done. So if the node has no predecessor, you need to borrow from its successor or merge from successor. Here's the thing. If the node has no predecessor, which means it's the head node in that particular linked list. So you have to deal with the successor. So either you borrow some element from its successor, or you merge the successor into this node, merge the entire successor into this node. So otherwise, if the node has a predecessor, then you deal with its predecessor. You either borrow from the predecessor or merge into this node into its predecessor. So the idea is, if the rule is violated, you do two things basically. If it doesn't have a predecessor or successor, you do nothing, because there's nothing you can do. If the node has predecessor, you deal with its predecessor. You borrow or you merge. If it doesn't have a predecessor, then you deal with the successor. Either you borrow or merge. Then after that, you need to propagate upwards. Then propagation may stop somewhere or may go all the way to the root. Just like the insertion, the propagation may go all the way to the root. And here, the minimum is a quarter of its capacity rather than a half. In some other documents, you may see the minimum is a half, but I want to make a little change. I want the minimum to be its quarter. I'll explain to you why. And here is the operation. So for deletion, you borrow from its predecessor. So you borrow from predecessor means you move the trailing elements from the predecessor and prepend to this particular node. For example, this is a node. It has too few elements. It's less than the minimum. And then the predecessor has quite some elements. Then you borrow, which means you prepend the trailing element from the predecessor to this node. The reason is the linked list is sorted. So when you move some of the trailing element from the predecessor and prepend, so you still keep the linked list sorted. So you borrow from the predecessor, or you merge into the predecessor. So merge into predecessor if the predecessor doesn't have many elements. For example, I set the cutoff value to be half. If it's no more than half, you merge the current node into its predecessor. Remember, when you do merging in the linked list, you always merge the node into its predecessor. When you're dealing with merging, you have two neighboring nodes. One is the predecessor, one is the successor. So you always merge the successor into the predecessor when you do merging. In this case, you just append all the elements of this node to the elements in the predecessor, and this node, and you reconnect the pointer. And this node is to be deleted. So this is the operation of merge into the predecessor. And here, what if it doesn't have predecessor? Then you have to deal with its successor. So here is the example. This node doesn't have predecessor, which means it's a head node in the linked list. The predecessor is null. So you borrow from its successor, which means you move the leading elements from the successor and append to this node. The reason is the linked list is sorted. When you append the leading element from the successor, you still keep the linked list sorted. And because it doesn't have predecessor, the zeroth element of this node is the sentinel. That's very important. It's a sentinel node. And what if you merge from the successor? So when you merge from the successor, you move all the node from the successor and append to this node, and you reconnect the pointer, and the successor is to be deleted. So that's merge from the successor. So okay, I mentioned before that the minimum is set to the quarter of its capacity rather than half. So why that's this case? So this is to avoid thrashing. It doesn't happen often, but it may happen in some extreme cases. The example is here. let's assume the capacity is 100, and it contains number from 0 to 99, and this node is full. Now you want to insert 100 into this node, and what happens? You have to split this node. So you actually create a new node after this node and move half of the elements to this new node. And then what happens, this node will contain 51 elements, and this new node will contain 50 elements. This is fine. But now, you insert 100, you split the node, then what happens? You want to delete 100. You delete 100, then this new node will have only 49 elements. Then it's less than the minimum. So you've had to merge. Then you merge, you delete delete the new node and merge with its predecessor to restore the original node. So you see what happens. One operation will cause the node to split, and another one operation will cause the node to merge. And in general, it's expensive to create or delete an existing node. So that can be a performance problem. So, but when you set the minimum to its quarter, and this situation can be avoided. For example, if you set the minimum to be 25, so when you insert a new node, you still have to split. But when you delete, well, you delete 100, the node still have 49 elements. It's still greater or equal to 25. You don't have to merge. So you have to delete another 25 nodes to trigger the merging. So this is why I set the minimum to a quarter of its capacity rather than half. And here is another question: is why to deal with its predecessor if it has predecessor? Here's the reason. If the predecessor exists, then either borrowing or merging into predecessor can fix the violation. That's one, which means the predecessor dealing with the predecessor is sufficient to fix the violation. So if you want to deal with its successor, then there is a situation that if the deleted element is at index 0, then what you have to do if you want to deal with the successor, then both the current node and successor are affected. You have to update the index of this node and the index of the successor in their parents, and they may have different parents. Okay, and this can be problematic. You will see in the node. The idea is for each level you affect only one node. When you affect more than one node, the coding can be complicated. So if there is no predecessor, which means the 0th element is a sentinel, and later you will see the sentinel is always there, which can never be deleted. So this situation will not happen for the node which does not have predecessor. So in this situation, you borrow from successor will not cause any issue. So what happens, after the deletion, you may have to propagate upwards. So how did deletion propagate upwards? If you borrow from the predecessor, and then you propagate to its own parent, and you need to update the index of the current node in its parent, because you change the index, you change the element at index 0. So if you merge into the predecessor, you also propagate to its own parent. And what you need to do is to delete the current node in the parent. So what happens if you don't borrow from its successor? If you borrow from successor, so you propagate to the successor's parent, then because the current node, you don't need to do anything on the current node, because the index didn't change. And but the successor's index changed because you changed the 0th element. So you can update to the successor's parent. You need to update the index in the successor's parent. What if you merge from the next? Well, you propagate to the successor's parent. You delete the successor in its parent. That's what you need to do. to propagate upwards. And here's the example. So you borrow from the predecessor. This is what happens. You prepend the trailing element in the successor. So you change the element in the zeroth index. So you can go to the parent, update the index. So what happens is merge into predecessor. In this situation, you append the current node to its predecessor. Then you reconnect pointers to delete the current node. Because this current node is deleted, you should go in the parent. You should delete this pointer in its parent. So what happens is you borrow from the successor. In this situation, if you want to borrow from the successor, you propagate to the successor's parent, because you update the zeroth element in the successor. You update its index. And remember, this is also a sentinel. The sentinel will never be deleted. It's always there. And what happens? You merge from successor. You append all the elements in the successor to the current node, and you reconnect the pointers to delete the successor. So you also propagate to the successor's parent, and you delete the node delete the pointer to in the parent node of the successor. And the propagation may go all the way to the root. Here's the example. You want to delete 48. This root has 4 elements. You want to delete 48. So what happens is you delete this pointer to the 48. So you have the root has only one child. When the root has only one child, you can redirect the root pointer to its only child, and you disconnect this pointer, and this old root will be garbage collected. You have a new root. This is a new root. So there are some sorts in the deletion. For the insertion, you have when the node is full, you do only one thing: you split. And you will see the split will not affect the zeros of the existing node, zeroth element of the existing node. But deletion is more complicated, because deletion may affect the zeroth element of the existing node. Then, in general, you have to deal with predecessor. In case it does not have predecessor, you deal with successor. So deletion is generally more complicated. But they do have something similar. They all start from leaf. Then, the operations start from the leaf. Then you propagate upwards. You from the leaf to its parent, and may go all the way to the root. So for insertion, is that possible to move some elements to its neighbors, to its sibling nodes? Well, yes, it's okay. You can do that, but it makes things more complicated. Just the splitting makes things easy. So another question: how to choose the capacity? In the example I showed you, the capacity is set to 4. In general, the capacity shouldn't be too large, of course, but you can consider the page size and the data size. So this is arbitrary. So can the minimum be some value other than half or quarter of the capacity? I think yes. Maybe 1/3 of the capacity, maybe it's okay. But I don't like the number 3. So I explained to you why I choose a quarter of the capacity rather than half. If you set to half, it will work, I'm sure. But the reason I choose to a quarter, is to avoid some extreme situation. So let's do a brief review on the requirements of the B tree. So every node except for the root has at least k children. I showed you how to do. If it violates this requirement, it will merge or borrow from its sibling nodes to fix this violation. So every node has at most 4k children, which means every node is a quarter full and full. So I explained to you why, to avoid thrashing. the node has at least two children unless it's itself is a leaf. I showed you before. When the root has two children, so you redirect the root to point to its only child. So because there's no reason for a root has only one child, then all leaves appear on the same level. Why? Because a B tree is layers of linked lists. So by this definition, you can see all the leaves on the same level, which means all the leaves have same height. So let's do some rough analysis of the performance of B tree. Let's assume it has n elements, totally n elements, and the capacity is k, as k elements per node. So the height would be log k base n. And for search, it's log n, because you do binary search in each node, and there are roughly that many nodes to go through. So this is log n. So for the insertion, the worst case, you need to locate the node at the leaf, which is log n. In the worst case, you have to shift the entire small array. Then there are at most that many arrays for you to shift. So it's the complexity will be log n plus k times log n. So that's the same thing for the deletion. Let's compare with a binary search tree, for example, red-black tree. In this B tree, it may waste up to 3/4 of space, because each node is between a quarter full and full. But of course, binary search tree, you can see it also wastes some space. Maybe half of the pointer is pointing to null. So it's not a very big deal in my opinion. But here are the advantages. So it's more cache friendly compared to the binary search tree, because it uses array to store the indexes and the data. And it's faster in some of the operations. For example, in some ranged operation, ranged search and deletion, because it's a linked list operation. It can be faster in converting from sorted enumerables. You can construct the sorted enumerable into a linked list, and from the linked list you go another level, and then the complexity should be log n, and faster in merging two B trees. So you are essentially merging two linked lists. Okay, this concludes the part 1 of the video. Thank you.